Hi guys, welcome to Young's Modulus. It's basically a way of saying a constant if lots of things come to line. So essentially we're talking about stress and strain today. There are 5 questions on the opening page, have a go at them. When you're ready, move on, the next page will have the answers. And again, if there's any reason why you can't get the right answer, and you're not sure where you make a mistake, send a copy of the question and what you've tried so far to me via email, and I will try and steer you on the right track. So, this question's a bit open-ended. Value of K, so we're talking about Hooke's law here. If we use a thicker spring, so if we use steel, for example, we make a spring that's thicker, we'll know that the K value will increase. So if we want to look at a line that's steeper, so the stiffness increases, we just use a thicker piece of steel, which is great, except for the fact that it's not a constant. So with the thicker piece of steel, you've got, it might be a shorter length, might be a longer length, it might have a greater surface area through a cross-sectional area, and lots of factors and changes. It doesn't really help engineers plan for things. So Young's modulus is a way of looking at things. It doesn't actually matter on the size and shape, it's the material itself. Now, to understand this, we need to look at 2 components: stress. So we're talking about tensile stress. It can be compressive as well, okay, that's important. I don't feel like I've drawn on the slide enough yet, so let me get my pen and highlight that. That comes up quite often and people forget that it's talking about Young's modulus, think it's something that they haven't seen before. So force per unit area, okay, so the force applied over a cross-sectional area, so newtons per square meter, which I've just given away what the units are, i.e. newtons per square meter, or pascals. Okay, I think I may have just recorded about 5 different versions of this slide. If you get a few weird versions, this is the one that should count. So we just looked at stress, now I'm looking at strain. So we're looking at actually what a material will do under tensile or compressive stress. So usually we're talking about a piece of wire, for example, how much will it stretch? Okay, so strain is a measure of change, very important. Oh, I've lost my pen. The change of extension. Often people use the start, so they put in a start extension, they put this in as the finish extension. That is incorrect, it's the change of extension. So Young's modulus, where it all comes together. So we looked at stress, looked at strain, and this is how it comes together, and this is our Young's modulus value. Okay, so it's a measure of the stiffness of a material. Now, that can be a good thing or a bad thing. You might not necessarily want a material to be too stiff. If you make something too stiff, it tends to become quite brittle, and then it therefore is unusable in any situation where there's vibrations. You might obviously want a material that can be compressed, heavily compressed, without changing its shape. So you will look for a material with high Young's modulus. Right, so where it all can come together, Young's modulus also has this lovely equation that comes with it. So Young's modulus equals the force times the original length, the cross-sectional area multiplied by the change in extension. And like always, the best way to do it is to have a try. Now, just before we have a try at one of the examples, here are some of the typical values. You don't need to know these, but it is kind of obvious to start with. Mild steel has quite a high Young's modulus, hence why it's used for construction so much. Copper, half the Young's modulus. You're starting to look at things here that it's becoming too elastic. It's not stiff enough to use in reinforcement, for example. Well, bone, well, there's a reason why. Bone is a lot more flexible than people give it credit for, hence why your bones don't break every time you jump off, 10 centimeter step. Plastic, obviously you'd expect plastic to be quite low, and rubber you'd expect that to be very, very low. Okay, very flexible. So, in this question, it's an exam question, came out of a paper. So, it's asking, and you might have, if you were paying attention right at the start of the slide, you would have heard me say something about that Young's modulus is used when you don't care or don't want to worry about what size and cross-sectional area of the material. That hopefully will give you a hint as the right answer. I'm just going to talk a little bit here just to fill some time while you're thinking. You can pause the video. And the answer, of course, is B. It doesn't change. It's the same identical material. Bit of a trick question there. Okay, so with this question, I'm going to model this one, how I'd expect you to answer it. So straight away, if I can find my pen, there it is. So start off with Young's modulus equals force, the length over the area times the change in extension. Okay, obviously we want force. There you are. I'll just turn it into an E by accident. Go with. I want to rearrange it. So we're going to Young's modulus, which is given to us in the question. Thank you very much. Now on that little chart I showed you earlier, it actually showed it as 120 GPa. So it's a fairly similar value. Okay, so rearranging area, change in extension divided by original equals our force. Okay, so in this instance, Young's modulus 1.16 times 10 to the 11. The area, so I'm going to run out of space very quickly, aren't I? So we'll have, I might put some brackets to make this even easier for us. Pi, now this is diameter, so 0.11 squared, pi r squared for the surface area, and obviously that is times 10 to the minus 3 because it's in millimeters. I don't know why I'm whispering, as if you can hear that properly anyway. Okay, now last thing of course before I run out of screen, oh, it's getting messy now, is what's our change? Our change is 1.76 to 1.8, so that will be 0.04 meters. Yes, that's correct. All divided by our original length, 1.76. Now, I'm going to have a sneaky suspicion that the answer is going to appear on the slide in 2 seconds, but try that anyway. Put that into your calculator and I'll press the button, see what happens. Ah, there you go. So the answer is telling me that that is 100 newtons. I'm going to hazard a guess that that's correct. Okay, so on this slide there are a whole bunch of questions, and hopefully I've given you a good lead. If you get stuck on any of these, as per normal, send me the copy of the question you're trying to answer, what you've tried, and I'll try and steer you. But take your time, watch the units. Units catch everybody out when it comes to Young's modulus, particularly when you start talking about temperature changes, etc. Right, the answers are apparently on the next slide, so I'm going to stop talking. There you go, there's the answers. Okay, another question comes up here. Oh, it's a good one. It's a derived equation. Great questions, and I'm assuming the answer is going to appear when I press the button. Yeah, that's what it looks like anyway. Good. The fact is, the only one with the Young's modulus in the right direction. Yeah, fine. Okay, and last but not least, a good slide to have in your revision notes. Mainly because it's handy when people are talking stress over strain. So Young's modulus, identifying that steep materials are brittle, very stiff though, hard to compress. So concrete, it's a great one. Doesn't like being stretched, but loves being compressed. Strong material is not ductile, fine, because obviously it doesn't have our lovely curve at the top. It just breaks, as opposed to our ductile material, which will have this here, our peak here, our elastic limit that we covered yesterday or the previous slide, and down here our plastic and rubber materials. Well, I'm trying not to classify them as plastic because they're not actually plastic. It's just a way of describing a material that has plastic properties. Guys, as per usual, go through the slide. Any questions, let me know, and there'll be some other stuff attached coming out to you tomorrow. Best of luck.